So hi everyone, welcome to the first Seismic Academy run by the University of Toronto Seismic Design Team. My name is Daniel. This is going to be Seismic Basics number 1, Intro to Earthquake Engineering. So just some ground rules for this lesson. You can type your messages into the chat and a moderator, Coda, is going to read through them. And then he'll decide whether or not it can wait until the end or if it's important enough to interrupt me right now. You can also message the chat if I'm kind of being quiet or if maybe my recording skipped and you want me to repeat what I just said. The presentation and the PDF of these notes, as well as the recording, will be saved to OneDrive and they'll be posted to our website in the same place where you signed up for this academy. So seismic.school.ca/hashtag/academy. Please, as I said, I've muted everyone. Please don't unmute yourself, just because then it'll be in our recording and it'll be a little weird. And just as a reminder, this is being recorded and it'll be posted as well. So a little bit about me. I'm a 4th-year civil engineering student at the University of Toronto. This is my 5th year on the team, including 1 year of co-op. Last year, I was the team captain of the design team at U of T. I'm lucky enough to have been to the past 4 competitions, and I'm looking forward to 2021 in Seattle, hoping it is able to go on. This is my first time teaching anything online or really teaching any kind of structured lesson, so please bear with me. I've practiced a couple times. Hopefully I'll do as good of a job as I can. And again, questions are always welcome. Just type them into the chat. If you never use Teams, you don't know where to find them, there's a little bar on the bottom, with all these bunch of icons, and there's one for the chat function. So what are we going to learn today? I've broken it up into three main sections. A little bit of fundamental context behind earthquake engineering, some basic ideas that are good to know for this presentation, but also in the future. Free vibration tests, how we can use them to find some basic properties of the tower that we built. And also response spectrum analysis, which is a much simpler way to find how a tower responds to an earthquake. So just starting off with this context. So for those of you who's maybe it might be their first time part of a team or learning about the competition, essentially you build a 1.5 meter tall balsa wood tower that weighs about 0.5 kilogram. You attach 8 kilograms of weights to it, which you can see are those rods going straight through our tower in the picture. And then you test it on a shake table as if it's an earthquake. So it's going to shake back and forth. It's going to experience those forces. You're going to try to withstand those forces. Usually you also design or you'll model your tower using a computer analysis software. So for example, this is our 2019 Vancouver tower, the picture, and then the equivalent SAP 2000 model that we made. So also, what is an earthquake? This is kind of really complicated, deals with like plate tectonics and the earth moving around. But for us, what we need to know is it's a base excitation. So it's going to move the building, and it's going to be based on displacement. The earth is going to move 1 meter, and the building has to move 1 meter with it, because that's what it's being supported on. It has some intrinsic properties, most notably the frequency content, which is I'll get into later, but it's basically just kind of what frequencies of building this earthquake is going to really impact. So just remember that earthquakes have something called the frequency content, and we'll explain that more later. It can be measured based on the displacement, velocity, or acceleration in what's called a time history, which is just what you see on the bottom. It just means, every point in time, you have a different value for whatever measure you're using over the whole length of the earthquake. So down there, that's the ground motion that we had, ground motion 2 for 2020. And you can see this is acceleration over time. So where are forces coming from in an earthquake? In normal loads, they're static, which means they don't change over time, and they're usually a result of applied pressures, like a desk pushing down on a floor. They're applied only in one direction, so usually you only have to worry about your maximum forces in one direction. A member is usually only in compression or only in tension. And it's applied at the point of contact, so where that desk touches the floor or where the wind is pushing on the building. Earthquake loads are quite different. They're dynamic, so they're changing over time. You might have a different acceleration at one time than another. And they're also inertial, so they're not as a result of something pushing on something. They're a result of mass being accelerated and resisting that acceleration. This is, as I said before, generated due to the displacement at the base. These loads are multi-directional, so an earthquake is shaking back and forth. You can have maximum displacement in one direction, then it'll come back around to the other direction. And so usually members that you might only have to worry about for compression, you might now have to think about compression and tension. have to think about both ways. You can't just design it to only be stiff in one way. For rigid bodies, so for like those masses you saw in the tower, the resultant of this, so where this force is being generated, can be simplified to just being generated at the center of the mass of that rigid object. So a really simple example, I have a building here with one floor with a center of mass where that red circle is, supported by two columns. So as the Earth is moving to the left, the mass is resisting it, and there's inertial force to the right. And you could think of this kind of like when you're on a subway or on a bus. As a subway or bus accelerates forward, you feel as though you're pushed back. And then when it comes to a stop, you feel like you're being pushed forward. And that's kind of that inertial force. So in the context of the competition, I know the angle isn't perfectly right, but if you imagine there's the displacement at the bottom, and then at each one of those masses, we have that inertial force going the other way. The reason we can just simplify it to the masses is that those masses weigh, 16 times the weight of the building, so they're generating most of that force. So important to know as background is how do structures usually deform in an earthquake? There's what's called a shear response, which you can see on the top left, and this is typical for shorter, stockier buildings, like a one-story warehouse. And you'll have the most amount of displacement between floors on the bottom, and then as you go up and up, you'll have less and less displacement. A flexural response, which is on the bottom left, is the opposite. This is what happens in taller splendor buildings, such as the tower. And as you go up and up, you'll have more and more relative displacement between the floors. You can also have structures that are a mix of the two with a transition from a flexural to a shear response, which you can see on the top right. And you can also see where I put the red circles, that's where it's transitioning from a flexural response to a shear response. If you imagine a building with a flexural response and you kind of turn it on its side, you can pretend it's kind of like a cantilever, just pushing down. And just same as a cantilevered beam, you're going to have compression on the bottom and tension on the top. So if you imagine, if this is your tower, and you have a column in the middle and on the outer edges, you're going to have the most amount of compression on the bottom. In the middle, there's going to be much less force, and on the top, you're going to have the most amount of tension. And it's going to come in useful later when we're thinking about our tower as just a little bit of a cantilever. What's also important is what's called the lateral force distribution. So this force is being generated throughout the tower, but eventually it has to all come back down to the base and get dissipated down to the ground, which means that these forces accumulate at the bottom. So you're going to have the higher stresses there and larger section sizes. So on the right, if we pretend that our building is still a bit like a cantilever, that's going to be this form shape, and that's going to be the associated bending moment diagram, close to zero at the top and then getting larger and larger as we go down. So that was just a bit of basic context. Now we're going to go into free vibration. You can see a free vibration graph on the top right. This is one of the free vibrations that we actually recorded, I believe, for 2019, the Vancouver Tower. And what this will allow us to do is find some basic properties of our tower, such as the period and the damping. So what is a free vibration? A free vibration is what happens when we'll fix the base of the tower. We'll put in all the weights, and we're going to excite the tower. So this means we can push it or pull it and just let go. And that's how we get those free vibrations. And this is kind of, you can imagine like those door stops where you accidentally hit it and it's just going to like boing, go back and forth and eventually come back to rest. And what we can do is if we measure and graph that response, so if we put, for example, a phone on the top of the tower, tape it down really well and use the accelerometer app, you'll get what's called a damped harmonic isolation. Big word, but damped just means it eventually goes to zero, which you can see, and harmonic isolation is just a fancy word in that it's sinusoidal. You can see those waves going back and forth. Speaking of waves, just to quickly go over some basic properties. If this is a sine wave over here, we have what's called the amplitude, which is just the maximum or minimum y value, whether that's displacement, acceleration, velocity, whatever you want. You have the period, which is going to come up a lot, which is the time it takes to repeat a cycle. And then you have the frequency, which is the inverse of the period, which is how many cycles you can do in a given time. So for example, we have a building with a period of 0.2 seconds. Its frequency is going to be 5 hertz, which is 1/seconds. Something that's really interesting that we can do is our towers are really complicated, but we can kind of simplify them in the most basic way into what's called the single degree of freedom model. It's called the single degree of freedom model because a degree of freedom is how something can move, and this can only move in one way, back and forth, as you can see in the image. And all this has is it has a certain mass at the top M, and then it has a member supporting it with a certain stiffness K, and this stiffness can depend on, how strong is the balsa wood you're using, how tall is your tower, what size are the sections that you're using. Bigger columns is going to be stiffer than skinnier columns. and also what's called damping C, which I'll also get into a little bit later, which refers to how fast your tower dissipates that energy and goes and like comes back to rest. So as I said, it only vibrates in one way, which is why it's a single degree of freedom. And it vibrates based on one period, T, which you can calculate very easily just based on the stiffness and the mass. And this period is really important. If you're going to remember only one thing from this presentation, it's that period governs the response of a single degree of freedom model, or really any model in an earthquake. So a stiffer structure, so for example, a shorter structure or a much stronger structure, it's going to have a lower period, and are going to have higher accelerations, lower displacements, and vice versa. A really tall, skinny tower is going to have much higher period, lower accelerations, and higher displacements to a given ground motion. And so just remember that we can simplify, whatever complicated model we have, whatever complicated deformed shapes, into just a single degree of freedom if we can characterize them based on the period. And then, as I said, damping. So damping is a structure dissipating energy. There's a lot of complicated ways this can happen. For example, it can be, sections being, moved, and then the molecules in the section heats up. It's a little bit complicated. Doesn't matter. What you have to know is just the structure dissipates energy. It's not going to vibrate forever. There's a key concept known as critical damping, which is the amount of damping you need to come to a stop the fastest. So it's that red line that you see in the graph. That's critical. That's when a structure is critically damped. You have overdamped systems, which they also don't oscillate. They don't go back and forth, but they just take longer to come to rest, which is the gray line. And then you have underdamped systems, which tend to oscillate back and forth. And you can see that as a dark blue line. Our tower is underdamped, and that's why you can see it going back and forth in the free vibration graphs that you saw before. What's nice is, because of some fancy math that I don't have to go into regarding differential equations, which we'll go over in a different Seismic Academy, this damping results in exponential decay. And the fact that it's exponential is really important because that allows for some math to be a lot easier later on. For a single degree of freedom system, this critical damping is really easy to calculate. It's 2 times the square root of the stiffness times the mass. So you can see on the top, on the right, when the damping of our actual tower C is greater than critical damping, it's overdamped. When it's the same, it's critically damped. And then when the actual damping of the tower is less than the critical damping, which is true for the competition, it's underdamped. In structural, we tend to define this damping not by that value C, but by it's called the damping ratio, which we use zeta for, the Greek letter zeta. And this is really simple. It's just the proportion of damping in our tower to critical damping. Typically in real buildings, so depending on if it's steel or concrete and some other properties, it's generally thought to be between 2 and 3%. For the competition tower, just from experimental testing that we've done in the past, we've found it to be between 1 and 4%. And this means it's really, really underdamped. It's really similar to that blue line that you see on the right. This damping ratio, it doesn't matter what ground motion you apply to it, doesn't matter what loads, it's intrinsic to the structure itself. It can vary by direction. So for example, the tower that you saw before that looked rectangular, we have a different damping ratio for the long side and for the short side. But it doesn't matter what ground motion we apply to it, the damping ratio for whatever side that we're pushing it on is going to be the same. The higher the damping ratio, the better, up to a critical damping. So we want to be as close to 1 as we can, just because then the vibrations damp out fastest. It comes to a rest. You have lower accelerations, lower displacements, as you'll see later on. Unfortunately, there's not much we can do when we're designing a tower to increase the damping ratio other than to add dampers, which we'll get into in a different Seismic Academy. This is kind of like you build the structure how it is, and you measure your damping ratio, and you hope for the best, hope for as high of a damping ratio as possible. So coming back around to free vibration, knowing what we know, so we'll push on the tower, we'll get it to vibrate, and we'll get this graph. Now, if we get the distance between these peaks, that's going to be the period of the tower if we pretend it's a single degree of freedom system. And what's nice is since damping is exponential, we can use what's called exponential decay to find the damping ratio of the tower using what's known as method of logarithmic decrement, which is really fancy, but we'll go over some more simple math in a second. And all you need to know for logarithmic decrement is just the relative amplitude of the peak. So if the first one is 1 G's of acceleration and the next one is 0.8 G's, that's all you need to know. And what this will let you do is calibrating your computer model to the built tower. Because usually how it works is you'll make a model in SAP 2000 or ETABS or something, and you're going to build that model. And then you're going to need to change your computer model to match up to the built model, because it's not always going to match. you're going to have to change your stiffness. So this could mean changing the stiffness of the balsa wood or changing the stiffness of the connections in your model to match the measured period of the tower. And then you can change the damping ratio of the tower to match your measured value. So how do we get the damping ratio? This looks like really complicated, but don't worry. The top part shows you how to get the logarithmic decrement, which is that delta, and use it to find the damping ratio. And this will work no matter what peak you want to use. If you want to use peak 1 and peak 3, peak 2 and peak 5, you can use this method. If you make it easier on yourself and you only use adjacent peaks, so you only look at the relative amplitude of peak 1 and peak 2, or peak 2 and peak 3 and peak 4, you can use this method on the bottom left, which all you need to input is to get the damping ratio is x0 and x1, where x0 is the relative amplitude of the first peak that you're looking at, and x1 is the relative amplitude of the second peak. And then what's really nice is our towers have really low damping ratios, and that allows us to make it even simpler. So it's going to be approximately equal to just the ln of the first peak divided by the second peak divided by 2 pi. And we're going to see in a second with this really quick example. So I have here 4 Fourier that we did for our 2019 Vancouver tower. And you can see they're all pretty similar, and you can see that nice exponential decay. And I took the first 3 peaks, I found the time at which they occurred, I found the normalized acceleration, which just means that I divided all those functions by the maximum acceleration. And the reason I did this is that sometimes I might push a little harder or pull a little harder. But what's really important is just what happens when we divide by that maximum acceleration to make them all kind of normalized, like a bell curve almost. And so knowing the times of those peaks, we can just subtract the times to get the period. And you can see the period is about 0.1 seconds approximately. And then I used on the left both the simplified formula and then also the approximation. And you can see, they match to 2 decimal places. So this means that for I believe this is the short side of the 2019 Vancouver tower, we would use a damping ratio of about 3.4, 3.5% in our model. One thing to note is that these free vibration tests can be really noisy if your accelerometer isn't that good, but also if there's significant what's called higher modal effects, which I'll get into in a second, or if there's significant torsion. So for example, this is the free vibration we got from the most recent year's competition because there's that significant torsional component. And you can't really see that exponential decay quite as well. You can see there's like these weird little mini peaks going on. You're not going to get as good numbers with this, and not going to be quite as reliable. What you're going to want to use to get the period instead is something called the sine sweep, which we'll go over in a future lesson. So you don't have to worry about that right now. Just know that this free vibration may not always work if you have some issues with your tower. So using those basic properties, we can characterize the response of the tower using what's called a response spectrum. So what is a response spectrum? So the key thing to know is that towers can have really complicated deformed shapes. They can move in all sorts of ways. But we can break it up and simplify it into what are called the modes, which is just a fundamental way a tower can move. So for example, one mode of the tower can be the cantilever motion. And you'll see in a picture example of this in a second. We can pretend all these modes are themselves their own single degree of freedom systems, just based on the period. And this is where we can use a response spectrum. We can use a response spectrum, which tells us the response of a single degree of freedom system to a ground motion, add all those responses of each of those modes together, and find the response of the whole tower. So why can we do this? The reason we can do this is actually because we can build up a ground motion. So if you add up an infinite series of sine waves, you can build up any function you want, and it's including earthquake ground motions. And what's nice is you can go the other way. You can find out which sine waves you used to build up that ground motion. And using something called a fast Fourier transform, which we'll go over it in a future lesson, what's key is you can find the frequency content of this ground motion. And what this means is if your structure has a certain frequency, like 5 hertz, and the ground motion is made up of a lot of sine wave of 5 hertz, that's going to be really bad. It's going to lead to what's called resonance, which I'll get into in a second. This frequency content really impacts the response of the structure, and it's intrinsic to each ground motion. So it doesn't matter what structure, a certain ground motion is going to have a certain frequency content. A different ground motion is going to have a different frequency content. So an example of this that I made really quickly is if you have those individual sine waves that I'm adding on the left, and then the cumulative function on the right, I can slowly add new sine waves to make more and more interesting shapes. And this just happens to be how you build up a square wave. So if I add up an infinite series of these, it'll be a perfect square or a rectangular wave. But you can do the same thing for a ground motion as well. So what is resonance? Resonance is what happens when that ground motion is really hitting the fundamental frequency of the tower. So the period at which the tower wants to vibrate, if the frequency quantum of the ground motion has a lot of frequencies in that range, it's going to resonate. That means that there's going to be amplification of how much the tower wants to vibrate. Really bad, do not want this to happen. You want to be as far away from resonant frequencies of the ground motion as possible. But what's nice is that if you have higher damping, it doesn't quite matter as much. So you can see on the graph on the right how much amplification you have depending on how much damping you have. So no damping, it's asymptotic. It goes to infinity. It's going to resonate forever. Some damping gets a little better, and the more and more damping you get, the less this resonance matters, which is another reason why damping is so good in a tower, because resonance matters less. And it's just a function of the input frequency, so what the frequency content of the ground motion is, and the fundamental frequency of your tower, which is if you pretend your tower is that single degree freedom system, what's the period of that system, the frequency of the system. Real towers, as we know, though, are multiple degree of freedom systems. They can move in all sorts of ways, not just one. They have, I mean, in reality, towers have infinite degrees of freedom and infinite modes. This is really complicated to analyze with computers. And each of these different ways that can move is called a mode of vibration. So hopefully this clears it up a little. A mode of vibration is kind of like, hopefully in high school physics, you saw that demonstration of the string that can move back and forth in different harmonic waves. This is the same idea. It's a way a structure can fundamentally deform in a standing wave. And the standing wave just means that those places where you have the maximum displacement, so for example, in mode 1, we have our maximum displacement at the top. In mode 2, you can see it somewhere around the middle. That location doesn't change, it just changes its amplitude. So it's going to go back and forth with the same place of maximum displacement. These modes are intrinsic to a structure, so it doesn't matter what ground motion you're applying to it, those modes are the same. And what's important to note is that each mode is going to oscillate with a different rate, which means each mode has its own period. So for example, the first mode might have a period of 0.12 seconds. The second mode is going to have a period of 0.05 seconds, and so on. It's really complicated to get these nodes. It's something to do with finding the eigenvalues and eigenvectors of the stiffness matrix of your tower. Complex stuff, a lot of linear algebra. Don't worry. What's nice is that if you model your tower on whatever software you have, SAP, ETABS, doesn't matter, robot, you can use modal analysis and get all the modes of your tower, as many as you want, with the periods, with everything. So that's how you get those modes. What else is that each mode is going to impact the structure differently. So a proportion of the structure's mass wants to move with each mode, and that's called the mass participation. Usually the more complicated the mode shape, the more points of zero amplitude, the more points of maximum amplitude you have, the higher the frequency, so the faster it vibrates, but also the lower the mass participation. And what's nice is that it's a proportion. So if you sum up the mass participation for all the modes, the infinite modes, that's going to be 100% mass participation, which means that's how your real tower responds. Generally, in the competition tower, your first mode, the cantilever mode that you can see on the left, has between 65 and 90 mass participation. So it's going to be really good at generalizing most of the structural response. What's nice about these modes is that we can break them up, as you can see. The period of that first mode that I talked about, the cantilever mode, is what's called the building's natural period, and the inverse is called the fundamental frequency. So when you break your tower up, that first mode, usually the cantilever mode, if it has a period of 0.2 seconds, then you'll say the fundamental frequency of the tower, or sorry, the natural period of the tower is 0.2, and the fundamental frequency is 5 hertz. How you know what number the modes are is based on their period. As I said before, each mode has its own period, and the first mode has the largest period, and on and on. Mode N, it's going to have the smallest period. And so they're going to vibrate with higher frequency and with lower displacements. What's nice is these modes are linear. And if you remember linear systems from statics or any other class that you may have had where you had to add a bunch of things up with linear terms, you can break them up and find the response of each of these modes separately. And then with a factor of proportionality, which is just based on the mass participation, so how much mass is moving with each mode is really high to impacting the proportionality factor. Add them all up, find the response of each mode, and add them all. When you add them all up, you get the actual deformation of the tower, as hopefully this image on the right demonstrates. So just to review what we learned, so for a single degree of freedom system, the period governs the dynamic response. And the frequency content of the ground motion influences the dynamic response a lot. A structure has infinite modes, but by breaking them up, we can approximate the response of the tower by just using as many modes as we need, using the modal superposition. So what are we going to do? We've built our tower in whatever model we want, SAP 2000, as I said before, ETABS doesn't matter. We found the different modes of our tower, and now we're going to find the periods of those modes. As I said, they all have their own period, and pretend they're single degree of freedom systems. So their response is characterized just by that period. We're going to use what's called the spectrum, which is the graph on that right, to find the maximum response of each single degree of freedom system. This could be maximum acceleration or maximum displacement over the course of the entire ground motion. And then we're going to linearly combine these to find a structural response. So what this response spectrum is really is it's summarizing how a single degree of freedom system of any period, but of a specific damping, responds to a specific ground motion. So as you can imagine, each ground motion is going to have a different response spectrum, and the damping ratio of the tower is going to also affect this response spectrum. And what you should note is that, when there's an earthquake, you're going to have a whole time history of the acceleration of that single degree of freedom system. What this graph is showing is just the maximum response. So for example, we look at a single degree of freedom system, 0.15 seconds, and we go up, we see that its maximum acceleration for the whole ground motion is about 4 Gs. There's different ways of combining these modes called SRSS, CQC, there's other ones. And they're used in different scenarios, like when your modes are really close together, when their periods are similar, or when their periods are far apart. You can find the calculations online. There's tons of different resources. A bit of a graphical summary, hopefully this will make it a little clearer, is we have each of those colored graphs is a response of one single degree freedom system for a whole ground motion. And what you'll do is you'll just find the maximum value that you want. So in this graph, you're looking at displacement, and put it on your spectrograph, which is that black graph. So we're going to go over a little bit of an example. People that are more familiar with this competition might know that the people that run the competition give us a response spectrum. However, it assumes 5% damping, which we think is probably a little bit too high for most of your structures. Although if you get 5%, that's great. It's better to use a response spectrum that's associated with your tower's damping ratio. What we use is something called Seismic by Seismosoft. You can get an academic license at that link below for free with no time limit. So I'm just going to quickly go over how to get one. I hope, can everyone see Seismic right now? Can someone just type in chat? I hope you guys can all see it. So I have something loaded in here now, but let's say I didn't. I'm just going to go open. Oops. Okay, Coda says we can do it. So I'm going to open. This is where the competition ground motions are. I'm just going to open the acceleration for ground motion 1 that the SDC gives us. Okay, so usually it gets it pretty right. My first line is line 2. My last line is whatever it calculates. This time factor is really important. Make sure it's correct. And then I'm going to change the units to be whatever I want. Usually I work in Gs, meters per second, and millimeters. I don't know if there's any Americans here, but if there were, you can change it to inches, something weird like that. I'm going to press OK. Takes a little second to load. There we go. And you can see the acceleration on top, the velocity. The space systems are a little weird because it uses double integration. We don't have to go into why this doesn't come back to rest. But what's important to note is this is our time history of the ground motion on top and acceleration. We're going to go over to this tab called Elastic and Elastic Response Spectra. And now let's just look at what happens with 3 different damping ratios, 1, 3.5, and 7%. I'm going to go into settings, and I'm going to say, let's look at between period of 0.08 to 0.2 seconds for our single degree freedom systems with a step of 0.01. Going to hit refresh. And so this is telling you there's no x-axis, but at this period, if our tower has a damping ratio of 7%, we're only going to get 0.7 Gs. But if we have a damping ratio of 1%, we're going to get all the way to 1.5 Gs. So this is showing you that the damping ratio of the response spectrum matters quite a bit. And then you can also refine this. You can only look at the damping ratio of the tower that we have. So let's say it was 2.5%, which we got before. And we can make this much finer. Refresh. And it's much smoother, right, which is much nicer. What's nice is we can save these spectrums as text files, as CSVs, look at them on Excel, do math with them that way. So that's how you use Seismic Signal, which, as I said before, you can get for free. Okay, so that's that. Now, how do we actually use this? So now we're going to go to Excel. So here I have a response spectrum from ground motion 1 from last year. So depending on the period of the system, we're going to have different maximum roof displacements. And the way this works is I have my modes from SAP 2000. So I built the structure in SAP 2000. I modeled all the weights and everything. And it told me for mode 1, this is your period, mode 2, this is your period, and so on. And what I'm going to do is kind of what it's showing on this graph. I see 0.129. I'm going to go down to where 0.129 is and see 3.68 is the maximum roof acceleration, the roof displacement, experienced for the whole ground motion. So you find the period, find the displacement or acceleration, or whatever value you're looking at, and read it off. So we're going to go through this whole thing. So 1.02, 2.63, 1.01, 2.52. You can obviously automate this with some kind of script. What's nice is that also most commercial software do this automatically for you, but I think it'd be good if you know how to do it. So 0.7, 1, 2, 2. Okay, so we have all of our different responses of each of those modes. We're going to use what I mentioned before as sum of the responses, the square root of the sum of squares. So we have all these responses. Now we're just going to square them all. So I squared that one. We're going to drag this down. Now I'm just going to add all of these responses up. And you can see these ones on the bottom, the higher modes, they matter much less. What's the square root of 0.0023? It's tiny, right? These first couple of modes dictate most of the response of the tower. And as I said before, the fundamental mode, the natural period, this mode number 1 is doing most of that. You can see it's 2 times as big when squared, as any other mode. So now we have the sum of those squares. All we have to do is take the square root, and there we go. This is our the response of our tower to the ground motion, to ground motion 1 2020. So this will tell us the maximum displacement or maximum acceleration of our tower for the entire ground motion. It's not going to tell us the response at every point in time, the time history. We'd have to do a more complicated analysis for that, but it'll just tell us the maximum. Okay, so that was that tutorial. And you might be wondering, how accurate is this? This seems pretty simplified compared to a real tower. What's nice is that it's actually pretty close. So this is our results from last year. We have, as I said before, that time history analysis, which is much more complicated, requires making sure your model is a lot better. You have to run this on SAP. You're not going to do it by hand. I have response spectrum analysis for both that CQC method that I mentioned and SRSS, and you can see, these are all pretty close. They match up quite well for ground motion 1 and ground motion 2, which are just 2 separate ground motions. And what's nice is in the competition, we actually measured these displacement acceleration for ground motion 1, and you can see it's not perfect, but it's pretty good, which is nice considering those models that we made are perfect, and the model that we built is it's going to have imperfections, going to have some eccentricities, things like that. I didn't put ground motion 2 because our model had some members break, which means the model is not linear anymore. Some of these assumptions aren't as valid. Don't worry about that. What's nice also is that this provides a good reality check. If your RSA and your time history analysis are giving 2 wildly different results, that tells you something's wrong in your model. So that kind of tells you how to calculate the response of your tower, how to get some of those properties that you need with variation, and some context. Remember, you can go to seismic.school.ca/#/academy for calendar of future sessions, the recording of this session, and all the resources like notes for this section. If there's any questions, feel free to ask them in the chat now. I don't see any during the session, but we're going to stick around for however long it takes to answer all these questions. Thanks everyone for attending. I hope this was helpful. All right, Dilly asks, can you explain one more time where you got the values for the different modes in the Excel spreadsheet that you're using? Sure. So let's go back to that. So these modes I didn't calculate by hand. What I had to do is I had to build a SAP model. So you can see in this slide, this model is built on a proprietary software called SAP 2000. You have to put in all the members, all the conditions, like it's fixed at the bottom, has those weights going through it. You have to put all that in, and then you do what's called a modal analysis, which the software will do for you. And it'll all of those modes with all the different periods, it'll tell you mass participation, all those different factors as well. So this is really kind of hard to get by hand. It's a lot of matrix math, a lot of linear data. But thankfully, whatever software, I believe UPC uses SAP 2000 daily for you guys. So you'll just, when you have the model made in SAP 2000, it'll tell you what your modes are.